All right, my MathCounts people, we're going to cover transformations for our transformation stretch that we're going to be doing in a little bit. So here we go. So we've got 4 different types of transformations we're going to look at today: translations, reflections, rotations, and dilations. So our first one is the most basic. So in a translation, we're just going to move a shape or a point left or right, up or down, without changing how it's facing. So if I take this and I start moving it around, it's still always going to be like increasing right there. It's going to have the same slope no matter what I do. So the slopes on this is going to stay the same. Let's do red. There we go. So slopes are going to stay the same. Because no matter how I move it, left or right, up or down, it's going to always stay facing the same direction. Now I've got a little problem here. I'm going to translate it right 4 and then down 3. So if I take each of these points and go right 4, 1, 2, 3, 4, and then down 1, 2, 3, A would move to here. We would actually call A prime, but whatever. Okay, so then we'd go right 4, 1, 2, 3, 4, and then down 1, 2, 3. And this would be the copy we call B prime. And here's what we see. We see that the facing has remained the same. And we have kept the same distance. From A to A, that is the same distance as B to B. So we're preserving some kind of distance here. Now there's a way to do these problems just looking at their coordinates and never having to graph it. If I'm translating right 3, what effect did right 3 have? Well, it added, right 4, what effect did it have over here? We're just adding 4 to the x coordinate. And when I went down 3, when we go down 3, we are subtracting 3 from the y coordinate. So the coordinate notation would be x plus 4, y minus 3. Why is this helpful? So you don't have to graph. So if I start off knowing that this point is at negative 2, 3, so this is negative 2, comma 3, all I have to do is plug it into this new equation that shows the transformation. So x is negative 2, so that'd be negative 2 plus 4, which would be positive 2. Y is 3, so 3 minus 3 is 0. And what do you know? 2, 0, that was that point right there. So we can use our coordinate notation to do these problems without even graphing them in the first place. So that's a translation. That's the most straightforward one. Left, right, left or right, so plus or minus on your x's, up and down, plus or minus on your y's. Reflection. This is the one where you can do a lot of stuff with it. Reflection is when we create a mirror image across a line, and what we're going to do is preserve a distance to that line. So the first one we're going to do is reflect over the y-axis. So here's my y-axis right here, and I'm going to reflect over that line. Now the y-axis is also the line x equals 0, because anywhere you cross this line, the x value is always 0. So anyways, we're going to reflect over that. So when we reflect, we take this point and we go across that line. Now, we have to stay the same distance from the line, and when we measure a point to a line, it always has to be perpendicular, so make sure that you move perpendicularly. That's a hard word. We move over 2 here, and we'll move over 2 here. So A and A prime are 2 units away from that line, perpendicularly. B is 3 units away from that line, so B prime would be 1, 2, 3 units away. And so here we get our first look at what a reflection looks like, and it looks like a reflection in the mirror, where everything's a little bit backwards, right? So it's not facing the same direction anymore. In fact, if you look at the slopes, you'll find out the slopes have changed their sign. This slope goes up 2 over 1, so that's a slope of 2 over 1. This one goes down 2 over 1, that's a slope of negative 2 over 1. So what I notice here between these 2 slopes is they are opposite slopes. So I'm going to just fill that in here. Every time that we are doing a reflection, at least over a vertical or horizontal line, we're going to see opposite slopes. Okay, so what is the coordinate notation when I reflected that? Well, let's look at the points. This point started at negative 2, positive 3, and then it became positive 2, negative 3, or positive 2, positive 3. So it looks like the y value did not change at all, but the x value changed its sign. So the coordinate notation would be negative x, comma, y. And we can just plug in this point right here. This is at negative 3, 1. So I'm starting at negative 3, 1. And so if I plug in x here of negative 3, negative 3 is positive 3, and the y value stays as 1. So 3, 1, and that's exactly where I had b prime at 3, 1. So we can see the coordinate notation is working for us. So negative x, comma, y is a reflection over the y-axis. Now reflecting over the x-axis, so here's my x-axis, and the equation of that one is always y equals 0, because anywhere you cross the x-axis, your x value on any point along this line is 0 for y. So this is the x-axis, or y equals 0. So if I want to reflect over the x-axis, I just do the same thing vertically. So I'm one space away, so I'll move one space away here, and there's my b prime. Here I'm 1, 2, 3 spaces away, so I'm going to go 1, 2, 3 spaces away. And we see again that we've got a mirror image where the facing is no longer the same. And if you found this slope over here, you'd find out that it goes down 2 over 1. It has the same slope as that one over there. So reflection over there. Now this time, let's look at this point. This point is negative 3, 1. This point is negative 3, negative 1. So the x value is staying the same. It's the y value that is changing its sign. So if we plug in 3, 1 here, or negative 3, 1, the x value keeps negative 3. The y value changes its sign and becomes negative 1. And that's this point right there, negative 3, negative 1. All right, what about reflecting something other than the x or the y-axis? Let's say, for instance, we want to reflect over y equals negative 1. Now, y equals negative 1 would be a vertical line going through negative 1 on the x-axis. So let's say that we wanted to reflect over this line here. Okay, so if I want to reflect over that line, I still just measure the distance to the line. So a prime would show up right here. And then b is 1, 2 spaces away, so I'd go 1, 2 spaces away over here. So there's my line, x equals negative 1, and I have now reflected over it. Okay, and again, the slopes are still opposites of each other. Now, the coordinate notation is kind of interesting for this one. We don't really have a notation for crossing when it's not an axis, but isn't going over this kind of like going over the y-axis? So what we could do is we could do several steps to get a coordinate notation for that. We're going to do that really fast because I'm going to show you a shortcut at the end here. So the first thing that I would do if I wanted coordinate notation is say, okay, what if I move the whole equation to the right one? If I move the whole equation to the right one, then our line of reflection would be on top of the y-axis. So I'm going to say, okay, I'm going to move everything to the right one. So this is going to be x plus 1, comma, y. Because I'm moving the entire graph one direction that way. So I'm getting my line x equals negative 1, and I'm putting it on top of the y-axis. Okay, now I'm going to reflect over the y-axis now. So when I reflect over the y-axis, the x changes its sign. Right now, x is x plus 1. So when you change your sign, you're multiplying by negative 1. So if I multiply all of this by negative 1 times x plus 1 is negative x minus 1, comma, y. Okay, so I moved the graph. That was to get it lined up with the y-axis. I reflected over the y-axis. But since I moved the graph here, I got to put it back in the right place. So earlier, I moved the graph to the right. So after I reflected it, now I want to move the graph back to where it should have been. So that means I got to go left. Now, if I go left, that means that over here, I'm going to go ahead and subtract 1 again. Because on a translation, if you go left, you're subtracting 1 from the x. So if I subtract 1 from this, I would get negative x minus 2 comma y. Now, let's look at the original numbers we started with. We started with, let's do this one here. This is negative 2, positive 1, 2, 3. So negative 2 comma 3. Now, let's apply this right here. So negative 2, that'd be positive 2. 2 minus 2 would be 0. 3, that stays the same. 0, 3. Oh, what do you know? It's that point right there. Now we've got the coordinate notation without having to actually do the reflection of the line. Now, what is the trick, you say? Well, the trick is if it's x equals negative 1, the x keeps its sign, is the one that gets its sign changed, sorry. The x is the one that gets its sign changed. And then this is twice whatever value this is. So if this were x equals 2, we would have had negative x plus 4 because we would double this value. Now, why am I doubling the value? Because I had to move twice. I had to move here, and then I had to move back. And in between moving, I was changing a sign. So this is move back. So if I wanted to reflect over y equals 5 instead of x equals negative 1, if I wanted to do it over y equals 5, so reflect over y equals 5, then the coordinate notation would be x comma y, so it would be negative y, double the 5 plus 10. Boom, done. Kind of cool. All right, last thing I want to show you is what does it look like to reflect over something that is not a vertical or horizontal line. So we're going to do that real quick here. We're going to do a really basic one where we're reflecting over y equals x. Y equals x, so if x is 1, y is also 1. If x is 2, y is also 2 because y equals x. So we're doing this one right here. So it looks like the line of reflection is this line right there. So that's my line of reflection. And let's say that I had a segment. Let's put one of the segments like right here, and let's put the other one right here. Okay, so there's my segment. The thing you have to keep in mind is when you are measuring distance to a line, you have to be perpendicular. So when I go across this line, I have to stay perpendicular to that line. So this point is one diagonal across, so I'm going to go one diagonal over this direction. You know, we all know this is root 2, and if you don't, you're in MathCounts, you're going to learn that eventually. So root 2 to here, root 2 to there. Over here, this is root 2 and a half, so it's 1/2 of root, or 3/2 of root 2. So here, root 2 and half, so I'd go half root 2 right there. And now I've reflected it across that line. Boom, boom, boom. Okay, so there's your reflections. Let's go to our third one, a rotation. So in a rotation, we are spinning a shape around a point. So we're going to preserve the distance to a point. The last one we were preserving to a line, now we're going to do it to a point. So if I want to go 90 degrees counterclockwise or 270 degrees clockwise, what I want to do is I want to take this shape and spin it this direction. So basically anything in this quadrant is going to end up in this quadrant over here. Now if I actually spin my paper, I can find out where it's supposed to be. Look at A. A is at 1, 3. Spin my paper. Now A is at -3, 1. So a 90-degree rotation, A would be at -3, +1. There's where A should show up. B is at 4, 1. Spin my paper 90 degrees. B is now at -1, +4. So -1, +1, 2, 3, 4. We have now rotated it 90 degrees. Now what I want you to see here is when you rotate it 90 degrees, these are now perpendicular to each other because it was a 90-degree rotation. That's why they're making 90 degrees, because 90-degree angle, you know, that stuff. Now everything's preserved its distance, so A is still the same distance away from the origin, because that's where I was rotating it over. B is still the same distance. If we did the Pythagorean theorem, we'd find out that these distances are all the same. Now let's look at some of the tricks for doing this. First of all, well, let's look at the points first. Let's look at this point right here. This point right there is 1, 3. Now let's look at A prime over here. A prime is at negative 3, 1. Look what happened. Let's look at B. B's at 4, 1. Oops. B prime is now at negative 1, 4. So we see the pattern here that's occurring is the y value is moving to the x spot and changing its sign. So we would write negative y, comma, and then the x value is moving to the y value spot, but keeping its sign. So this would be negative y, comma, x. So we don't need to do it. We could do it here. This is the pattern for 90 degrees or 270 degrees. Okay, so the other thing I want you to see is look at these slopes. This one goes down 2 and over 3, negative 2 over 3. This one goes up 3 and over 2, positive 3 over 2. These slopes are opposite reciprocals. They're opposite, meaning their sign has been changed. Reciprocal means the numerator and the denominator have been switched. And that's always going to happen with a 90 or 270. Okay, the other quick way that I do these is this one was 1, 3. If I know I'm going 90 degrees in this direction, I know I'm going to have to end up in this quadrant. So instead of going 1, 3, I switch the two values. 1, 3 becomes 3, 1, and I put it in this quadrant, 3, 1. I'm not worrying about negatives because I know which quadrant it's supposed to be in. So I just do 3, 1, there's that point. This is 4, 1, so I'm going to do 1, 4 over here. So I'm just switching the x and the y, knowing which quadrant I'm supposed to end up in. Okay, next one, 180 degrees. Well, that's just another 90. And if I do another 90, I know that I'm going to end up in this quadrant here. So this A is at 3, 1. So instead, I'm going to go 1, 3. This B is at 1, 4. So I'm going to go 4, 1. So now we've taken this one and gone 90 and another 90, and now we're in this spot here. Now this is another 90, so I'm still going to do another negative yx. Now if I take this y, which is now the x spot, and move it over here, I would get negative y in the y spot now, because it used to be x was negative y, and then I'm going to move this one over to this spot and get negative x. Remember, because when we do 90, whatever's in the y spot changes its sign and moves to the x spot. Whatever's in the x spot moves to the y spot. So it looks like I get negative x, negative y. And that's exactly what I'm getting here, because this point here is at 1, 3. This point right here is at negative 1, negative 3. This point here is at 4, 1. This point here is at negative 4, negative 1. See, negative x, negative y. And then, of course, if I would do another 90 degrees, that would be 270 degrees. And you might have guessed what's going to happen now. Now we're going to get y, comma, negative x. And so if we go this direction, again, doing all of our 1, 3, we can do 3, 1, because I know it's supposed to be in this quadrant. And this is 4, 1, so we're going to go 1, 4. That's going to be in this quadrant. Looks like we're making a square, doesn't it? Well, it should look like that because these are all 90-degree angles. Each 90-degree turn makes a 90-degree angle. All right, so this one was A prime, prime, prime. This is B prime, prime, prime. This is prime, prime. All right, so there's our rotations. Our last one is called a dilation. Now, every other shape or transformation we've done so far is what's called a rigid motion, where it's keeping the same size. So everything that we made is congruent. It's all the same size. A dilation is different. This uses proportionality to either grow something or shrink something. So we're either going to enlarge or reduce our segments or whatever we're dealing with. So here I'm going to dilate with a scale factor of 2 about the origin. Scale factor means the proportion. So this says I'm going to make something that is twice as big. Now, we're starting at the origin here. So everything doubles. So if I'm going up 1 over 1 to get to b, I double that. And I go up 2 over 1, 2. And here would be b prime. Over here, I'm going backwards 1, up 2. So I'm going to go backwards 2, up 4, because my scale factor is 2. I am doubling that. And this would be a prime. Now what we're doing is we're comparing our distance to the copy over the distance to the original. So this is root 2, and this is 2 root 2. So from here to here, that's 2 root 2. And the distance to the original was root 2. So these cancel out, and we see there that's our scale factor. So we're just doubling the distance to from the origin to the copy, and then compare it to the origin to the original, and it's doubling. Now the other thing I want you to see here is when it radiates out like this, it's always going to radiate in a line. It's kind of like a projector screen. Like say this is the projector and it's going towards the screen. Light travels in a straight line most of the time. So here we've got, you can bend light, but anyways, here we've got going over here, we can see that just like a projector coming from the light bulb, it's just going to radiate out from that point, and all of our dilated points will always end up on a line between there. Now, what's happening between these points? Well, this point was 1, 1, and now it is 2, 2. This point was negative 1, 2, and this point is now negative 2, 4. So what's happening with our dilation? This is 2x comma 2y. So when I dilate about the origin, whatever my scale factor is, I just multiply the coordinates by whatever the scale factor is, and that tells me where the new coordinates should be. So if I'm dilating with a scale factor of 1/3, that means I'm shrinking. I should get 1/3 the size. So we said earlier that if you're going to dilate, you can draw a line between the point of dilation and your point, and the new point should show up somewhere on that line. And same thing with B. If I draw a line through B, the new point should show up somewhere on that line because we're dilating according to this point. It's like the projector is projecting out towards the screen. Now 1/3 means that I'm getting smaller. If we've got a scale factor of 2 up there, that means I'm twice the size. Now everything is going to be proportional in here. So what I should also see is the distance of AB should get 1/3 the size. Right now it's 1, 2, 3, 4, 5, 6. It's a distance of 6 here. So if I dilate it by 1/3, I should see that it has, the size is now down to 2 because it's a ratio of 6 over 2 is, or 2 over 6 is 1 over 3 there. So what I'm going to do is I'm going backwards 3, up 3. So I'm going to take 1/3 of that, and it's going to be up backwards 1, up 1. So A prime should show up here. For B prime, of course, it should show up right there. So now it's 1/3 the size. And we can count it. Here's 2. That's 6. This is 1/3 the size of that one. So we notice that we've got 1/3 x, comma 1/3 y. Now, the real fun stuff is when you do a translation or you do a reflection and a dilation, or you do a rotation and a dilation or something like that. That's where it gets really fun, and you can make equations based on the different transformations you're making. We're not going to do that now. I'll let you play around with it. So the slopes on this, they're always going to be the same. So we're always going to create something parallel when we do that. All right, that's all I got. Ooh, 25 minutes. That was a little bit long. Sorry. All right, bye-bye.